Okay. So yesterday we kind of went through, or last class rather, we went through and talked about kind of the history of our operating systems and how we got to where we are today, and talked about kind of how operating systems break down into individual pieces, and that's more of an operating systems class subject in terms of the high level. What we care about is how do we interface with operating systems? How do we talk to those individual pieces? So we talked last time about the kernel and file systems and memory systems, and we didn't go into tons of details in some of these things, but a lot of them are topics that should be covered in 350 in the operating systems class. So we don't really need to go into details with them other than understanding that these things are part of our operating systems. And when we write stuff to disk and we read stuff from disk, that's a system call. When we have a process, and that's, so process management is something I do want to talk about a little bit today, because that's really a pretty important aspect of what we're going to do in the second half of this class. So let's talk about that for a few minutes. What's a process? As it relates to operating systems, what's a process? Okay, yes, it would be. It's a program that's running. Think of it as an application, whatever. Something that you double click. When you double click on something, at least one process is born. Okay? So these are things running. What does it mean for a process to be running on your computer? What's the side effect of that? How does your computer run a process? Okay, so a process loads into memory. Okay, so let's kind of draw a picture of this. So if we draw a picture of our computer, we have our CPU here, right? And then sitting up here, we might have our RAM. Okay, and then we have maybe your hard drive, solid state drive, whatever. So long-term storage, short-term storage, CPU, you have your I/O peripherals and things like that. So let's just call this I/O stuff. And all of that is kind of glued together by buses, let's just say. Okay. So when we double click on a program, that program goes from your hard drive into RAM, right? Some aspect of the program. It might not be the entire program, it might be some aspect of it, depending on what memory management type you're using. Modern day, we typically use a paging type algorithm, but whatever. It's in RAM, so it's fast. All right. Once it's in RAM, what happens with it? Once it's in memory, is it just good, or does somebody actually have to process it?
It's got to run on the CPU. The CPU processes.
All right, so this dude, this CPU is kind of, we think of it as like eating code, right? We have so when stuff leaves RAM and goes to the CPU, it's coming out in machine language, or we could think of it as assembly language, a low-level language. One-to-one relationship with the CPU, right? CPU's collection of magic tricks, all that jazz. All right, so this CPU is going to feed off of those, those things. Now, our modern day CPUs, are they single core, or usually are they multi-core type processors? Multi-core. What does a multi-core processor mean instead of a single core processor? What's the ramifications of being multi-core? 2-core instead of 1-core, let's say. Well, you can do more than one thing at once. It might not necessarily be more than one process, but certainly you can do more than one thing at once. Now, keep in mind, the whole idea of a computer is that our CPUs are really, really, really fast. So at the very least, we get faked out as the end user that we think, at the very least, we think more than one thing's happening at once because they're happening so quickly, right? But then as our computers have gotten faster and faster and faster, we now have CPUs that can do literally more than one thing at once. Dual core, quad core, and even within that, we have these kind of hybrid-y type things where you heard of something called like hyperthreading. Hyperthreading is a fancy way of saying, when you look at if you have a quad core with hyperthreading, a lot of times it'll show up as 8 logical cores. I would call it 6 functional cores because each of those hyperthreading cores allow you to do kind of like an extra half instruction. It has to do with how if you think about your CPU as like being this really big fat guy, okay, so it's something not like me, something else, all right, and so the fat guy doesn't want to get up off the table and go up to the buffet, so the buffet comes to him, all right. We want to get stuff feeding into the mouth as quickly as possible. So with hyperthreading, we're able to kind of get that next bite kind of queued up, so that it's falling into your mouth as you're swallowing the previous one, something like that. And the funny thing is that is a pretty good example, like a pretty good metaphor for what's actually happening. All right, we're trying to get instructions into the CPU as quickly as possible. When's the CPU at its slowest? What's it called when one process is loading onto the CPU and another process is leaving the CPU? We want to minimize this to maximize the speed of our computers. Who? Deadlock. Well, deadlock is when you keep having to load things over and over again and never actually make progress. So that's really bad. So you answered the question right, but it wasn't the answer I was looking for. Because one process doesn't get 100% of the CPU forever, right? If you have Microsoft Word launched, you don't want Microsoft Word to get 100% of your computing power, then you can't listen to your music or something like that, or you can't check your email. You expect that regardless of how many cores you have, you expect that each one of your applications is going to get a little bit of CPU time. And then it leaves the CPU and something else comes onto the CPU and this guy gets back in line and waits his turn again. And then that's all happening so fast that we don't necessarily know the difference. We just feel like everything's happening at the same time. So what's that process known as when we have one process coming onto the CPU when another process is leaving the CPU? It's a major, major slowdown point in operating systems. Called context switching. Remember that? You learned about that, right? All right, so context switching is, I like to think about it like you go into a hotel room, you unpack your bags, 5 minutes later you repack your bags and leave. It's not very efficient. Okay. Now, the worst case scenario is when you have an application that has to do I/O too quickly. So context switching can either happen naturally. The process gets onto the CPU, it gets its 100 CPU cycles, let's say, and then the CPU says, okay, your time is up. Go get in the back of the line. That's okay. That's a necessary evil. We have to have context switching. Processes come onto the CPU, processes leave the CPU. Now, bad context switching is when, and it could just be sheer luck, when a process is currently working, the CPU is currently working on a process that's working through each line of assembly code and it hits an I/O instruction. So it's waiting for the user to give some input. Well, how long might it take for the user to give their input? Who knows, right? So since it's waiting for something from the user, it would not be in our best interest for the CPU to sit there and just wait. We want our CPU to be working as close to 100% of the time as possible, which is kind of funny since our CPUs sit idle about 93% of the time. Something in that ballpark. But our goal is to have it working 100% of the time. All right, so if we have to wait for anything, we're going to context switch the current process out and bring something else in so that particular process that's waiting for I/O can go into the wait loop and get its I/O and then get back in line when it's ready. Okay, so the worst case scenario, an example of where we would have kind of the worst performance would be when a process spends the time to get onto the CPU. So it walks into the hotel room, unpacks its bags so that the CPU can pick up where it last left off, reload all the hardware registers, that kind of stuff. Then the first instruction is an I/O instruction. So as soon as he's unpacked his bags, he immediately has to repack his bags and get off the CPU because he has to go do I/O. Horrifically inefficient. We wouldn't do that in real life, right? We would, but instead, we can't necessarily look ahead. We can, but in the generic terms, we're not looking ahead at what the next instructions might be. Okay, sometimes we might do dynamic process management where we try to make a process leave the CPU at an opportune time. So let's say you're 2 instructions short of your CPU cycles, yet you hit an IO instruction. Maybe you go ahead and break then. Maybe you are, if you go 1 extra cycle and you hit that IO instruction, then you have a natural break. That's going to keep you from wasting a lot of time next time. So you might decide to go ahead and give that process an extra cycle to let it get to its IO instruction. So it's his idea to leave the CPU rather than the CPU kicking him out. Something like that. So there's things we can do. But in any case, context switching is very expensive. Now, this is more of an operating system issue than something we care about. But what we care about is the idea of processes as a systems programmer. So what does that mean? When we have this CPU, all right, so we have this CPU, and let's just look at a dual core type system. So we have technically 2 different CPUs, right? And these CPUs are handling some processes. Shrink this guy down. All right, something like this. So generically, we would say these guys are resources, right? In computing, they're a very important resource, but they're not the only resource. When we think about operating systems and how computers work, if you have 1 bank of memory, and if 2 things need to store stuff to memory, you have to have some way of managing who gets access to that resource at that particular time. Well, right now we're talking about a pretty important resource being the CPU, and we have 2 of these guys. So if you go into McDonald's during the lunch rush, which line do you get in? You get in the shortest one. Okay. Sometimes you might pick and choose depending if there's like a family of 12 there with you have like the mom and like 11 kids. You're pretty sure that's going to be a long order, right? Okay, as opposed to one line might be longer, but you figure it might be the shorter line. So, but in any case, you try to pick the most efficient line to get into. Now, that's a pretty easy decision, right? Sometimes you regret it. Sometimes if I got on that line, I would have gotten served a little bit quicker. But generally speaking, it's an easy decision because your order has no impact on somebody else's order, correct? You don't have to wait for this person to order their cheeseburger before you can order your Big Mac. It's not, the order of operation isn't important. Now, when it comes down to scheduling for CPUs, especially when we have multiple processes within a single application, you might have a chicken or the egg problem. You might have to have something occurs in one application or in one process before another process is even allowed to get CPU time. If this process right here is waiting on the value that is being computed by this process right here, this guy cannot get onto the CPU because it's going to try to read a value from a memory location that doesn't exist. Kind of make sense? And that comes down to process scheduling. All right. Again, these are operating system concepts, but it's something that we do need to be concerned about when we're writing this stuff. So we're kind of, as system programmers, we're taking advantage of these different things. Now, if we imagine a program where more than one thing can happen at the same time. So, for example, let's say, we'll just do another picture here. Let's say we're writing a web server. What does HTTP stand for? We've seen this before, right? At least seen it. It's all here. Look. So this guy. Okay, well, this has a little S on it, which means secure. Okay, but HTTP, Hypertext Transport Protocol. 2 out of 4. All right, so now these are things from the very, very early days of the internet. We have FTP and HTTP and Telnet and SSH. You always heard of all those things? So HTTP, what is that? Is it just a fancy name that decided to pick those letters, and then we decided it's hypertext transport protocol because we had to give a name to the acronym, right? Surely couldn't they have come up with something that kind of rolled off the tongue a little bit better than HTTP? Anybody know how HTTP ultimately works? I've definitely taught this in a class before. I would think many of you have had it. We've probably talked about Restful APIs in conjunction with this.
It's a series of instructions are basically ways of sending information to tell the server when it needs to return information or update stuff.
Okay, so a web server is a system, right? It's a simpler system than a whole big operating system, but it's a system. All right, what do web servers do? We use web servers all the time. We don't necessarily write web servers, but we use who's the client of a web server? We're not the client of the web server. The browser. We're the client of the web browser. The web browser is the client of the web server, right? So what do web browsers do? When we type into our web browser www.google.com and press enter, what happens?
It directs you to the correct site.
So that dude, that browser, at some level, regardless of, so more pictures. So we have our web browser. And then we have our person. Okay, pictures for person? Aw. I was hoping I was getting pretty pictures. All right. Whatever. So whoever human talks to the web browser. All the way over here, we have our web server. All right. Now this web server knows how to speak the HTTP protocol. Okay. Hypertext Transport Protocol. That's the language that he speaks. Just like we're conversing in English, these two guys are conversing in HTTP. All right. Now, let's kind of shift this stuff over here. Now, what do you think? Do you think a web server would be a difficult program to write? What if our assignment for Friday was to write a web server? Would that be a friendly assignment? Yeah, not really that bad of an assignment. Web servers are pretty easy. What does a web server do? Well, a web server is a program running on a computer that effectively manages the file system and this file system has a bunch of files that live on it. So maybe you have home.html. And maybe you have another file, user.html, so on and so forth. Yeah, you might have another file like register.php, something like that. So a web server manages the file system, which has a list of files. So what does the web browser do? The web browser says, he makes a request for a file. And this guy is called a GET request. All right. HTTP has 4 functions: get, post, put, and delete. All right. So there's our GET function. So we're asking for something. The web server is going to receive that request, and then he's going to look in his file system and say, is that file there? So maybe we're looking for, we'll just say we're going to get home.html. That's what we're requesting. What's HTML? Hypertext Markup Language. Okay, that's what it stands for. What is it?
Basically code that tells how to make something, or how something should format display.
Is HTML a programming language?
Yeah. Sort of. Some people say it.
If you learn programming from me, is HTML a programming language? Why? What kind of language is HTML? Well, it is a markup language. What kind of language do I teach it is? Which is the correct answer. Data representation language. Right? It's a data representation language. It actually is the correct answer. But I have, of course, invented it in the internet. I'm just showing you how the internet works here. Al Gore is a liar. So in any case, HTML is it stands for Hypertext Markup Language. It's a data representation language that allows you to represent pretty pictures and text, right? Now, who understands HTML? Web browsers. So this guy receives HTML and turns it into pretty pictures and text, right? All right, so this guy right here is going to receive a stream of HTML. If we want to be completely accurate, it's going to be HTML and JavaScript. Those are the two things that a web browser knows how to deal with. All right. This is client-side logic. Now, why do we need JavaScript? Why do browsers support JavaScript? Well, it is a loosely typed language, but that's why they support it.
Well,
like, look, I don't have a loosely typed language, so I need one.
It does logic.
Oh, why does it need to do logic? Because HTML is not a programming language. HTML can't do the logic itself. It represents data, so it needs a logical-based language in order to do client-side logic. Make sense? So you see how everything just adds up to the truth? Can't make this stuff up, people. All right, so no matter what the web browser asks for, he's always going to get back HTML and JavaScript, right? And then he's going to do his thing and spit it on the screen as your pretty pictures and text and moving parts if it's a JavaScript-y based thing. And JavaScript has really evolved over the years. Now we have kind of JavaScript on steroids now with Ajax and jQuery and all this other stuff, which are just fancy names for JavaScript libraries. They're all still JavaScript. Somebody spent a lot of time writing really kind of cool JavaScript functions, and they put a funky name on the front of it. And now people, I'm into jQuery or Ajax. Now you even have server-side JavaScript stuff to make the web programmers who were used to do stuff on HTML. Now they can do Node.js stuff and blah, 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 blah. All right. But in any case, no matter what the web browser asks for, he's going to get back HTML and JavaScript. So if the web browser makes a request for home.html, the web server is going to look at his file system. He's going to try to read. He's going to first do a directory listing, right? So he's going to ask the operating system, maybe the web browser or the web server rather. He's in control of like maybe a folder called public underscore HTML or something like that. It's kind of the go-to one for Apache. Apache's a famous web server, let's say. All right, so he's going to look in that thing and say, give me a directory listing. Now, do any of these files match the thing this guy's looking for? We've got a match right there, right? All right, so we have home.html. Now, the web server is going to then ask the follow-up question. He's going to say, do I need to do anything to this file? It's going to look at the extension on the file, also known as a MIME type. We've heard of MIME types before? So the extension on a file tells us what kind of file that is. So if you see somebody sends you an email with an attachment that's a .doc, what program, if you double clicked in that file, what program do you think it's going to open? Word. So when you double click on that, Windows uses the MIME type of that file to determine that Microsoft Word is the file that is the program that should be open to read that file. Make sense? That's what a MIME type is. All right. So the web browser is going to look at the MIME type of home.html. It's going to decide this guy's MIME type is something called text/HTML. Doesn't matter. That basically says it's already in HTML. And it just so happens that that's exactly what the web server's job is to send back. So he doesn't have to do anything special. All he's going to do is he's going to read this file in from the directory and spit its contents out over the stream as HTML. And it's going to be this dude's job to interpret that HTML. Make sense? All right. Now, what if we asked for register.php? This guy's going to do a directory listing. Are we going to find a file named register.php? Yep. What's the MIME type of that guy? Not text HTML? Something else? Okay, what is PHP? Yeah, loosely typed programming language, typically a web-based language, typically used for server-side processing. Over here, we're on the server side. So the web server is going to say, this guy's a PHP program. So presumably the output of a PHP program would be HTML and JavaScript. So, but a bunch of logic is going to happen first in order to ultimately spit out that HTML and JavaScript. So the web server is going to say, I need to go ahead and run this program. So for PHP, this web server is probably going to have a PHP module, PHP mod. All right, so he'll toss that file over there for pre-processing. He'll get the output of that file and then send the output over back to the web browser because the output is presumed to be HTML and JavaScript. Make sense? All right, so this is how a web server works. Not too bad. We're basically doing directory listings, reading files, and writing files over. So assuming we know how to do, network programming stuff, this isn't such a horrible thing, right? Now, tell me, do most web servers? Well, let's go this route. So, how many people hit Google every second? For rounding down, the correct answer is a lot. Right? Okay, so a lot of people hit Google every single second. Now, how long do you think this register.php file is going to take to run? Probably some fraction of a second, but not zero time, right? Okay, it adds up. So what if I just happen to be first in line? And you're number 2. Okay, you're waiting for Google to respond to you when it's done with me. All right, and then let's say we got a little infinite loop issue here in our register.php file. So that fraction of a second program is having a little bit of a rough time. All right, so which one of you who probably wrote that? Who wrote that file? No, you didn't write that. You didn't put an infinite loop into the code, did you? Maybe. All right, so we got a little bug in our program here. We got an infinite loop, so that means you're never going to get served by Google because it's stuck on fulfilling my requests. The PHP modules are sitting there waiting for my HTML JavaScript output to come from this infinite loop program. And maybe they have a built-in timeout function after, 8 seconds or something like that. It finally kicks out now. Now keep in mind that you're number 2 in line, but there's 100,000 people behind you, right? Do you think that's the way the server works? Think it's a first come, first serve type situation? But we hope not, right? When you go on and you do a search on google.com, you expect results quickly. Now, sometimes the internet's a little sluggish, right? That's more of your internet problem rather than Google's thing. How many of you have heard of a denial of service attack? Learn about that in the networking class, or not networking, the security class. So denial of service or DDoS. What's the second one there? This is the one we usually see, right? We usually see this, but yet we pronounce it denial of service. Yet this is the denial of service. This guy's a newer kind of animal, a cooler kind of animal. Since the internet's become a big, big, big thing, this is a distributed denial of service attack. So how does denial of service work? We're bombarding that server with requests. So first of all, evidence would suggest that the Google server probably, or web servers in general, probably do not operate on first come, first serve. They're able to take a request from me, and while it's working with me, it's waiting for another request from somebody else. Correct? We'll talk about how that might work here in a few minutes. So what a denial of service is that we keep making request after request after request to the point that the web server gets overwhelmed, where, behind the scenes, if you just have that web server running on a single computer, there's only so much memory, so much processing power, so much this, that, and the next thing, that it's going to end up getting bogged down. And what we end up having up here is the CPUs that are on that server get overwhelmed with having all of these processes backed up, waiting for CPU time, and nothing ever gets done. Does that make sense? Now, that's a denial of service attack. That means it's coming from one source. Now, one source can only send stuff so quickly. You're at the limit of how fast your computer, so if I set up a denial of service attack from my laptop and you're the web server, I can only send information to you one thing at a time. Or maybe if I have 2 cores, I can send it two things at a time, right? Okay, but I still have a limit on just how big of a hell I can make your life. That's why I install my virus on multiple machines. Okay, so all of those machines are all attacking you. So I have 1 million cores, all sending you requests just to waste your time. That's a distributed denial of service attack. So most of our denial of service attacks today are that, so it's kind of become just DDoS. That's denial of service, but actually it's, get it? All right. See, every class it's gold. It's just this stuff. It's so good. Jonah, right? Yeah. This is all because of you and your infinite loop here is the issue. All right. We saw that coming. All right. So, all right. In any case, let's see. So, getting back to HTTP, because here's kind of a cool punchline for us, which I have taught in some classes, and the fact that nobody remembers it is troubling, but whatever. I get paid either way. In any case, so this HTTP thing has been around since day one of the internet, right? In the early days of the internet, it was kind of synonymous with the web, with the web browsers, right? That was what the internet was. There was other tools that lived and died with the internet. Anybody have ever used a tool called Gopher? Gopher was actually one of the official early internet protocols. It was kind of like a search engine before search engines existed. So it was a different system. It wasn't through a web browser. It was a Gopher database, if you will, for looking up stuff. Lived and died, blah, 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 whatever. So HTTP has been around for a really, 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 really long time. Now, realistically, HTTP, for all those years the internet's been around, we only have really used 2 of its functions. We've used GET requests and we've used POST requests. All right. What a GET does, sometimes, let's say you're passing a username. So let's GET versus POST. So a GET request, if we're passing a username with a GET request, it might look like http www.login. Let's do just .blah.com/login.php. Might look something like that. Whereas the post version of this is going to look like, why did it capitalize that? will look like that. Nope. Trust me. Okay. So a get sends the information as part of the URL. All right. Maybe not the end of the world for a username. Probably wouldn't want to have credit card information up here or passwords, that kind of stuff. But username, not the end of the world. Okay. Now a post, what happens is you have a packet that gets sent. Okay, a form that gets sent along with a post request. And those pieces of information are sent in that form. Now, that doesn't mean they're encrypted. It just means that they're not conveniently visible in the URL. If you were using a packet sniffer or something and you read the HTTP packet, you would see what the username and the password and all that stuff is. That's why typically you want to look for that little S, HTTPS for secure. That uses something called SSL, Secure Socket Layer, to encrypt all stuff that's going back and forth between the web server. So at that point, post would be better because your form is an encrypted form at that point, whereas your URL isn't going to get encrypted, so you'll always see username as plain text. But now what's nice is a get is something very easy for us to recreate. If you're writing software and you need to make a get request, you can just create a string that looks like this. Do a little concatenation, everything's peachy, right? Okay. Where creating a post request programmatically is completely doable, but you have to start using you either have to use some network libraries that make life a little bit more difficult, or like we were talking yesterday, there's some third-party things that allow you to build post requests more conveniently. All right, so in any case, these are two functions from the HTTP protocol that have been used for years and years and years and years. When we go back here, we saw there's two other functions of HTTP that have basically gone unused. Oops. Maybe at some point somebody used them or something like that. But now what we've done is, so over the years, how many of you have heard of something called an API? Okay, API, kind of a either abstract programming interface or application programming interface. It kind of gets used interchangeably. Doesn't matter. It's effectively a set of functions that are provided by some application for external use. That's what an API is. Our operating systems have APIs. System calls. We're going to be working with those quite a bit, right? So in any case, you might have a let's say PayPal. You might use PayPal's API to send and receive payments or check an account balance, stuff like that. All right. Now, historically, when a company had some information they wanted to make available to programmers, they would have to write a proprietary. Oh, that's not right. Proprietary API. All right, they have a proprietary API. So they would have to teach whoever's going to use the API the exact way to speak to it. Make sense? All right. So we'll call these one-off APIs. So didn't follow any sort of standard. Okay. Then we started looking at standards for APIs. And one of them that became popular was something called SOAP. All right. And what they did with SOAP is they said, here's kind of a common way for you to organize your API so that other people can conveniently digest it. All right. Now, the issue there is you didn't have real great adherence to the SOAP standard. And part of that was because the SOAP standard was kind of a loose standard. Just says, it's a decent idea to kind of do it this way, if you want. Okay, nobody was really enforcing it. So for a long time, we had SOAP APIs. Now, the cool kid today is something called a REST API. Sometimes they're called RESTful APIs because that's like kind of more fun to say. It makes you really sound smart, like, oh yeah, I work a lot with RESTful APIs. Now, what is a RESTful API? How many of you have heard of REST APIs or RESTful APIs before? So that's the current cool kit. What is a REST API? Must be a standard. It's in my list of under standards, right? I've also said it's the cool kid, so probably must be better than SOAP. What makes something a REST API? It's like awesomeness based on history. What the REST API, what the standard says, it says, you know what? We have this protocol. It's been around for a really long time. It's got 4 functions associated with that protocol. Only half of them really get used on a sort of regular basis, but who cares? Now, do you think that the HTTP protocol has been time tested? Probably works. Okay? It's a reliable protocol as opposed to random protocol X that kid in basement just invented. So if we can piggyback on top of the HTTP protocol, that would be a good thing. Okay? And what they decided is, you know what? What do we do with APIs? What are some of the stuff we might do with an API? Well, we might want to request information from if we're thinking about PayPal. Maybe we want to get a list of recent payments. Okay? Maybe we want to create a new payment. Maybe we want to delete an existing payment. Maybe we want to change the parameters of an existing payment. So now any company that has a REST API is saying, we're going to implement all of our endpoints in terms of these 4 functions, the HTTP protocol. So that means that any networking third-party application that's existed ever, since networking existed, since HTTP existed, which is since the internet started, any of those already know how to talk to RESTful APIs because they already speak HTTP. So all we need to do is make the appropriate HTTP calls to the appropriate endpoints to get our data. So maybe we make a request using GET. So maybe we do something like, I'll finish up here in a second. So we do something like, something like that. We go to the user payments endpoint, passing a user ID, and it gives us a bunch of payments. You're probably going to need some sort of credentials in order to get that stuff from PayPal, but as a general rule, that kind of thing works. All right, makes sense? All right, for Friday, go ahead and work through chapter 1 in the book. Everybody should have the book by now. Do all the interactive stuff for chapter 1. Most of it's going to be review, but you'll start seeing, what's up? Oh, chapter 2 then. Hold on, let me look at what chapter 2 is. This is all programming fundamentals, so you just start to see the programming stuff. Are you sure I gave you chapter 1 last time, even though that?
No, you just said look through it.
Oh, okay, well then I'm ahead of everybody.
Introduction and stuff.
So do as much as you can.
Yeah, definitely do all of chapter 1. So if you haven't already done it, go through chapter 1, read through these examples, do all the interactive stuff. Everybody should have the book by now because we're going to start doing C stuff here pretty quick. All right? See everybody on Friday. Don't forget the Bible homework is due on Friday.